Hey guys, I'm Katie Berkeland, and skimming through the topics covered by this class, I couldn't help but be drawn to Fourier transformations. I had heard of them previously, but I didn't know what it did at all. A few lectures later, I think I have a decent grasp on Fourier transforms, mainly what it is and why it matters. So let's see if I can't pass on some of that info. In its most basic definition, a Fourier transform is a mathematical transformation that takes a function in space or time and converts it into a function of frequency. While this doesn't initially sound like a big deal, it's found a lot of practical uses since it often converts data into something easier for us humans to interpret. For a specific example, think of a cardiogram which measures electric potentials made by the heart. A lot of these measurements, though, are going to include junk from other sources besides your heart, making it hard to distinguish which signals are actually relevant. Doing a Fourier transform on your raw data, though, gives you a graph much easier to filter. Now you can remove noise from outside a certain frequency range since the graph is now in terms of frequency. These Fourier transformations also found similar applications in a variety of fields such as quantum mechanics, signal processing, and spectroscopy, the last of which I'll explain later. For a brief history, in the year 1822, a Frenchman by the name of Joseph Fourier published a paper titled The Analytical Theory of Heat, in which he made some interesting claims. Of interest here is his claim that any periodic function could be represented by a sum of other harmonic functions. This was expanded on later by the works of other prominent scientists such as Lagrange, Bernoulli, and Euler. Their work led to what we now know as the Fourier transform. Mathematically, equation 1, as shown, is the Fourier transformation of a function f of x. Similarly, equation 2 is the inverse Fourier transform, where the lower k represents wave number. Using these two equations, you can take a function in terms of space or time and make it into a function of frequency. So, looking at an application, we have IR. Background infrared spectroscopy, called IR for short, is an analytical method used by chemists like myself. It helps us to determine the chemical bonds present in a sample. What it involves is exposing your sample to IR radiation and measuring resultant atomic vibrations. This will generate data which can be compared to known data. IR isn't perfect though. Its resolution isn't all that high, it's a slower method, and it suffers from a lot of interference. Luckily, we adapted, introducing FTIR, Fourier transform infrared spectroscopy. This allows a light source being splitted by a beam splitter. This will send one beam to reflect off a moving reference mirror and another to reflect off your sample. The beams then recombine, make an interference pattern, and are read by the detector. The detector will then turn that data into an interferogram. This machine collectively is the interferometer. The data collected from the interferometer then undergoes a Fourier transformation via a computer to give us the FTIR spectra we're actually after. Here's an example interferogram. Note that it's in terms of space, millimeters. The data, as you see, isn't really useful in that state, but we can change that. Let's say that this interferogram is modeled by this equation here, where this theta is the Heaviside step function. Let's transform this. So firstly, the underlined part here is just a shift in the wave number domain of k naught. What this means is that we can find the transform of the rest of the equation, then shift the result by k naught to account for that underlined term. So to simplify things, I recommend changing f of x to f prime of x, which does not include the underlined term. So that fancy f indicates our Fourier transform, which we're applying to f prime of x. Plugging in our f prime of x to equation 1 from before, we get this integral. This integral needs to be split because of the Heaviside step function, which means is that from negative infinity to 0, that function will equal 0, but from 0 onwards to infinity, it will equal 1. So we can split this into two integrals representing each of those domains. Conveniently, the leftmost integral simply equals 0, leaving only the rightmost integral to work with. By factoring x out of the exponent, we can get something that integrates as follows. Nicely, this infinity term goes to 0, and it just leaves behind our final Fourier transformation of f prime, 1 over g plus ik. Recall our modification of f of x, though, that the initial shift in wave number can be accounted for by including that shift in our final transformation. This means we need to change f prime of x back to f of x by substituting k minus k naught in place of k. And that's our Fourier transformation of f of x. However, remember that we're dealing with this in the context of spectroscopy measuring real frequencies. This means we need our function to have real numbers only. Luckily, there's a way to do that. The real portion can be found by adding the transform of f and the complex conjugate of the transform of f and then dividing that sum by 2. Our first step then is going to be finding that complex conjugate here in orange. So let's convert our transform into a form easier to work with. Start by removing that I from the denominator by multiplying by 1, then simplify the result. In this form, the complex conjugate can easily be found by changing the sign of the I term. Since we have the transformation and its complex conjugate, we can proceed to finding the real portion of the transform. Using the equation from earlier, we substitute our functions and we get something a little ugly. Luckily, it all reduces to a much simpler function, depicted here in orange. That is the real portion of the Fourier transform of our interferogram function f of x. This is what we wanted. So we have our interferogram data, and through a Fourier transform, we get that graph on the right. It's a function of space changed to a function of frequency. Now, the graph on the right might not look to be useful, but it's actually packed with a lot of useful chemical data. The peaks correlate to specific bonds, and we cross-reference these with tables from trusted sources. For instance, it's well established that the vibrations resulting from oxygen-hydrogen bonds are in roughly the 3700 to 3600 inverse centimeter range. And the other peaks give similar bits of info, alluding to a carbon-oxygen bond and a carbon-hydrogen bond. This makes perfect sense. This is a graph for methanol, after all. Methanol structure is given over here, with the bonds color-coded to their respective peaks. This is an extremely useful method for identifying the chemical makeup of samples, and it's one I personally can attest to the efficacy of. Analytical chemistry would be a heck of a lot harder without this tool in our toolkit. This is to say, thanks, Fourier.